The roar of four mammary engines echoes across the runway as Japan's first heavy bomber, the Nakajima Shinzān, struggles down 4,200 ft of concrete. At 44,330 lb empty weight, it's 8,000 lb heavier than America's B-17 Flying Fortress. The test pilot fights sluggish controls as the massive aircraft finally claws into the sky, climbing at barely 500 ft per minute, half the rate of an American bomber. In the hangars below, Chief Engineer Kenichi Matsumura watches through binoculars, his notebook filled with calculations that should have predicted this moment. Japan had purchased the Seoul Douglas DC-4E prototype in 1939 for $275,000, convinced they'd acquired the blueprint for America's aviation supremacy. 2 years of reverse engineering, hundreds of skilled workers, the best materials Japan could allocate, all to build their own version of American excellence. But as the Shinzān disappears into the morning haze, barely maintaining altitude, one devastating truth becomes clear. Sometimes copying American technology isn't enough. You have to understand why America built it that way in the first place. The morning sun cast long shadows across Oda Airfield as Kenichi Matsumura adjusted his stopwatch, preparing to witness what Imperial Japanese Navy headquarters believed would be their answer to American strategic bombing. The date was April 8, 1941, and the massive Nakajima G8N Renzan sat at the end of the runway like a metallic mountain, its four mammary engines already warming with deep throaty rumbles that vibrated through the concrete beneath his feet. Matsumura had spent 18 months overseeing every rivet and wire of this aircraft, driven by a singular obsession that had consumed Japan's aviation industry since Pearl Harbor planning began. The Americans possessed something Japan desperately needed: the ability to strike industrial targets 2,000 km from their bases. The B-7 Flying Fortress represented everything Japan lacked: reliable engines, defensive firepower, and most critically, the operational range to carry the war to enemy soil. Standing beside the runway, clipboard in hand, Matsumura watched Major Katsuaki Kira complete his pre-flight checklist in the Shinzān's cockpit. The bomber stretched 138 ft from nose to tail, its silver aluminum skin gleaming in the early light. On paper, the specifications looked formidable: 4,000 kilos of bomb capacity, 3,500 mm of range, defensive armament positioned to shred intercepting fighters. The Navy's procurement officers had called it Japan's war winner, the aircraft that would bring American industry to its knees. But Matsumura's engineering notebooks told a different story, filled with calculations that had been troubling him. For weeks, empty weight, 44,313 lb. The captured B-17G intelligence report showed American bombers weighing just 36,135 lbs without fuel or ordnance, 8,000 lb heavier for the same mission, a discrepancy that violated every principle of aircraft design he had learned in his 20-year career. The mammary engines reached full power with a sound like sustained thunder, each of the four radials producing 1870 horsepower, 7480 total horsepower to lift 62,60 lb at maximum takeoff weight. Matsumura did the arithmetic automatically: 20 horsepower per $1,000 lb. The B-7G achieved 133 horsepower per $1,000 lb with its Wright Cyclones, and those American engines had proven themselves reliable through hundreds of combat missions over Europe. Major Kira released the brakes and the Shinzān began its takeoff roll slowly at first, then with gathering momentum that seemed to take forever. 1,000 ft down the runway, 2,000 ft, 3,000 ft. Matsumura's stopwatch showed the bomber consuming 4,200 ft of concrete before the nose wheel finally lifted. A B-7 needed 2,200 ft under similar conditions, half the distance for twice the reliability. The Shinzān climbed at what could only be described as a grudging pace, gaining altitude at barely 500 ft per minute, while Major Kira fought controls that responded like they were submerged in thick oil. Through his binoculars, Matsumura could see the pilot's helmet moving constantly as he compensated for the bomber's tendency to wallow through the air rather than fly with purpose. American B-7s climbed at 900 ft per minute, their crews reporting that the aircraft felt eager to reach bombing altitude. As the Shinzān disappeared into the morning haze, struggling to maintain its labored descent, Matsumura finally understood the magnitude of Japan's mistake. 2 years earlier in 1939, Japanese negotiators had purchased the Seoul Douglas DC-4E prototype for $275,000, believing they had acquired the blueprint for American aviation supremacy. The massive four-line airliner had seemed perfect for adaptation to military use. 40 ft of wingspan, all-metal construction, tricycle landing gear, and 4 powerful engines arranged in the same configuration as the B-7. But the DC-4E had been rejected by American Airlines, deemed too complex and expensive for commercial operations. United Airlines, Eastern Airlines, and American Airlines had all examined the prototype and concluded it was overbuilt, over-engineered, and fundamentally unsuited for profitable service. The aircraft that Japan thought represented the pinnacle of American technology was actually American, industry's most expensive failure. Matsumura's team had reverse-engineered every component of the DC-4E with meticulous precision, assuming that American design philosophy emphasized brute strength over efficiency. They had reinforced structures that were already overbuilt, added defensive positions that increased weight without improving capability, and installed engines that produced adequate power, but lacked the reliability needed for sustained combat operations. The mammary radials failed every 50 flight hours, requiring complete overhauls that consumed irreplaceable materials and skilled labor. Wright Cyclones in American service routinely operated for 400 hours between major maintenance. The irony was devastating. Japan had spent 2 years and millions of yen copying an aircraft that Americans had abandoned as commercially unviable, then made it even heavier and more complex in the name of military adaptation. Every calculation in Matsumura's notebooks confirmed what the morning's flight test had demonstrated. The Shenzan was fundamentally flawed. A magnificent example of precision, engineering applied to the wrong foundation. Radio static crackled from the control tower as Major Kira reported his position 20 minutes into the flight service ceiling tests would come later. But early indications suggested the Shinzān would struggle to reach 24,000 FT under combat conditions. B-7s routinely cruised between 25 and 30,000 FT, using altitude as their primary defense against intercepting fighters. The American bombers operated in an altitude band that Japanese fighters could barely reach, turning the sky itself into defensive terrain. As Matsumura walked back toward the engineering hangar, his mind was already working through the implications of the morning's failure. Japan needed strategic bombers desperately, but copying American technology had proven insufficient. The DC-4E purchase had been based on the assumption that acquiring enemy hardware automatically transferred enemy capability. But capability resided not in blueprints but in the industrial philosophy that created those blueprints. American aircraft designers did not simply build flying machines. They built flying machines that could be manufactured by the thousands, maintained by minimally trained mechanics, and operated reliably under combat conditions by 20-year-old crew members. Japanese engineers built masterpieces that required constant attention from skilled craftsmen. Aircraft that were technically sophisticated but operationally fragile. The Shenzan would never enter production. Even as Major Kira completed his test flight and prepared for landing, Matsumura knew that Japan's first attempt at copying American strategic bombing capability had failed before it truly began. But failure, he realized, might teach lessons that success could never provide. Spring arrived at Nakajima's Kisumi facility with renewed urgency driven by Imperialis. Navy headquarters' unwavering conviction that Japan's strategic bomber program could still deliver victory. Despite the Shinzān's disappointing performance, Admiral Isoroku Yamamoto's staff had issued new directives that bordered on the impossible. Develop a heavy bomber capable of reaching the American mainland within 18 months, or watch Japan's window of opportunity close forever. Kenichi Matsumura found himself working 16-hour days. His engineering team expanded to over 200 specialists who had been pulled from every major aircraft project in Japan. The Navy's faith in the Shinzān remained unshaken, based on specifications that looked impressive when typed on official procurement documents: 4,000 kilo of bomb capacity, $3,500 mi of operational range, defensive armament consisting of 420 mm cannons and 12 7.7 mm machine guns. On paper, the aircraft seemed capable of devastating American industrial targets from the Aleutians to California. But Matsumura's flight test data told a different story, one that grew more troubling with each mission. The Shenzan's maximum speed of 261 mph made it vulnerable to any modern fighter aircraft, while its service ceiling of 24,450 ft left it exposed to interceptors that could attack from above with impunity. American P-38 Lightnings, according to captured intelligence reports, could reach 39,000 ft and achieve speeds exceeding 400 mph in diving attacks. The engine reliability problems proved even more devastating than the performance shortcomings. Mamori radials required complete overhauls every 50 flight hours, consuming aluminum alloy that Japan could barely afford to allocate. Each engine contained components machined to tolerances that demanded Japan's most skilled workers, men who were desperately needed for Zero fighter production as the war expanded across the Pacific. Worse, the memory power plants generated severe vibrations that loosened instruments, cracked fuel lines, and fatigued airframe structures at an alarming rate. Right. Cyclones and captured B-17s, by contrast, showed wear patterns consistent with 400 hours of operation between major maintenance. American engine design philosophy emphasized reliability over peak performance, accepting slightly reduced power output in exchange for dramatically improved operational availability. A B-7 squadron could maintain combat readiness for months at a time, while Shinzān bombers would spend more time in maintenance hangars than on combat missions. Matsumura's team had begun conducting detailed examinations of Wright R-1820 engines removed from B-17s shot down over the Philippines, and the differences in manufacturing philosophy were immediately apparent. American cylinders used simpler cooling fin designs that could be mass-produced on automated machinery, while Japanese engines featured complex cooling patterns that required individual hand finishing by master craftsmen. American connecting rods were forged from standardized steel alloys, while Japanese rods used exotic metals that improved performance but created supply chain bottlenecks. The fundamental problem extended beyond individual components to the entire industrial approach. American aircraft manufacturers designed for mass production from the initial drawing board stage, creating aircraft that could be assembled by workers with minimal training using standardized tools and procedures. Japanese designers optimized for performance and craftsmanship, creating aircraft that required skilled artisans at every stage of production. The result was bombers that performed magnificently when new but degraded rapidly under combat conditions, requiring constant attention from specialists who were increasingly difficult to replace. By summer of 1941, the Shinzān program had consumed resources equivalent to building 300 fighters, yet produced only 6 prototype bombers. Production rates that seemed adequate during peacetime planning proved catastrophically insufficient as the war expanded beyond anyone's initial projections. American factories were already delivering B-7s at rates of 20 aircraft per month from single production lines with multiple facilities planned for activation as military orders increased. The weight problem that had plagued the Shinzān from its first flight continued to worsen as additional equipment was installed. Armor protection for critical systems added 1,200 Li. Improved defensive armament contributed another 800 Li. Self-sealing fuel tanks, essential for survivability over enemy territory, increased empty weight by 1,500 pounds. Each modification that improved combat capability reduced the aircraft's already marginal performance, creating a vicious cycle where improvements made the bomber too slow to avoid the threats it was being protected against. Matsumura's calculations showed that a fully loaded Shinzān, carrying maximum fuel and ordnance, would struggle to maintain altitude if even one engine failed. Twin-engine flight characteristics bordered on dangerous with single-engine performance that made successful landing attempts questionable at best. B-7 crews, according to intelligence reports, routinely brought damaged bombers home on 2 engines, sometimes even returning to base after losing half their power plants to enemy action. The aluminum shortage that began affecting all Japanese aircraft production in late 1941 struck the Shinzān program with particular severity. Each bomber required 8 tons of aluminum alloy, compared to 5 tons for a Zero fighter or 3 tons for a typical Army bomber. Japan's total aluminum production capacity could theoretically support 12 Shinzān bombers per month, but only if no other aircraft were manufactured simultaneously. The reality of wartime priorities meant that heavy bomber production competed directly with fighter programs that were desperately needed for homeland defense. American aluminum production, according to intelligence estimates, exceeded 900,000 tons annually by 1943. Japanese production peaked at 142,000 tons in 1944, creating a resource gap that made large-scale bomber production impossible, regardless of design efficiency. Even if Matsumura's team had created a perfect aircraft, Japan lacked the industrial capacity to build it in meaningful numbers. The psychological impact on his engineering team became increasingly apparent as test flights continued to reveal fundamental problems. Workers who had spent months perfecting individual components watched helplessly as their craftsmanship was negated by systemic design flaws that could not be corrected through incremental improvements. The Shenzan required complete redesign from first principles, but Navy procurement schedules allowed no time for starting over. By autumn, Matsumura had reached a conclusion that he dared not voice in official meetings. Japan was building the wrong aircraft using the wrong methods for the wrong strategic situation. The Shenzan represented everything that Japanese engineering did well: precision manufacturing, attention to detail, optimization of individual components applied to a mission that required everything Japanese industry did poorly. Mass production, simplified maintenance designed for reliability rather than perfection. The captured B-7 sitting in Japanese hangars offered daily reminders of a different approach to aviation engineering, but understanding American design philosophy and implementing it were entirely different challenges. Japan had the technical knowledge to build better bombers, but lacked the industrial infrastructure to build enough of them to matter strategically. The captured B-7E arrived at Nakajima's facility on a flatbed truck convoy in March of 1942, its aluminum skin bearing scorch marks from the fighter attack that had forced it down in the Philippines. Kenichi Matsumura stood beside the hangar doors as workers carefully maneuvered the intact bomber inside, feeling a mixture of anticipation and professional dread. For 18 months, his team had been reverse engineering the DC-4E prototype, assuming they understood American design philosophy. Now they would finally examine the real thing. The Flying Fortress looked smaller than expected, its wingspan of 103 ft seeming almost delicate compared to the Shinzān's massive 138 ft spread. But as Matsumura's inspection team began their systematic examination, the true differences became apparent in ways that challenged every assumption about American engineering. The B-7's empty weight of 36,135 lb was 8,000 lb lighter than the Shinzān, despite carrying similar defensive armament and fuel capacity. Matsumura personally supervised the engine removal process, watching as technicians carefully extracted the Wright R-1820 Cyclone radials that had powered this particular fortress across thousands of miles of Pacific Ocean. Each engine weighed 1,850 lb and produced 200 horsepower at takeoff settings. The Shenzān's memorial engines weighed 2,100 lb each and generated 1,870 horsepower, creating a power-to-weight ratio that seemed impressive until compared with American efficiency standards. The Wright Cyclones showed wear patterns that told a remarkable story of operational reliability. Cylinder walls displayed even scoring consistent with hundreds of flight hours, while connecting rod bearings showed minimal degradation, despite obvious combat stress. Most shocking was the simplicity of the cooling system design: straight fins machined with automated equipment, rather than the complex curved patterns that Japanese engineers had assumed were necessary for adequate heat dissipation. Tearing down the American engines revealed manufacturing philosophy that contradicted everything Matsumura had been taught about precision engineering. Tolerances were looser than Japanese standards would accept. Yet the engines operated more reliably than mammary radials built to much tighter specifications. American designers had apparently optimized for consistent performance rather than peak performance, accepting slightly reduced efficiency in exchange for dramatically improved maintainability. The airframe construction differences proved even more enlightening. B-17 wing spars used aluminum extrusions that could be mass-produced on rolling mills, with reinforcement concentrated at high stress points rather than distributed throughout the structure. Japanese engineers had built the Shenzan wings using complex forgings that required individual machining, creating parts that were theoretically superior, but practically impossible to manufacture in large quantities. Matsumura spent hours examining the B-7's electrical systems, marveling at the standardization that allowed any component to be replaced with minimal training. Wiring harnesses used color-coded insulation and standardized connectors that eliminated guesswork during field maintenance. Control cables were routed through accessible channels with inspection plates at regular intervals, allowing mechanics to identify and repair problems quickly. The Shenzan's electrical systems, by contrast, required specialized knowledge to service with custom connectors and hidden routing that made troubleshooting a time-consuming process. The defensive armament installation revealed another fundamental difference in approach. B-7 gun positions were designed for rapid installation and removal with standardized mounts that could accommodate different weapon types as mission requirements changed. Ammunition feeds used simple mechanical systems that rarely jammed, even under the stress of violent maneuvering. Japanese defensive installations emphasized precision and firepower, with complex hydraulic systems that provided superior accuracy. Butte required constant adjustment by skilled armorers. Flight control systems in the captured fortress operated through cables and pulleys that seemed almost primitive compared to Japanese hydraulic boost systems. Yet American pilots reported excellent handling characteristics under all conditions. The mechanical controls provided direct feedback that allowed pilots to sense approaching stall conditions, while hydraulic boost systems could mask dangerous flight attitudes until recovery became impossible. Simplicity, Matsumura realized, was not a sign of inferior engineering, but evidence of superior design philosophy. The fuel system design demonstrated American priorities with brutal clarity. B-17 tanks were constructed from simple aluminum sheets with rubber bladders that could be replaced in field conditions using basic tools. Self-sealing capability came from rubber, compounds that automatically close small punctures, providing protection without complex mechanisms that could fail under combat stress. Japanese fuel systems used sophisticated pumps and valves that provided precise fuel management, but created multiple failure points that could strand aircraft far from home bases. As his team compiled their analysis through the summer of 1942, Matsumura began to understand the magnitude of Japan's strategic mistake. American engineers were not building individual aircraft. They were designing production systems that could manufacture thousands of aircraft using workers with limited training. Every component was optimized for mass production, field maintenance, and operational reliability, rather than peak performance or engineering elegance. The numbers told the story with devastating clarity. B-17 production had reached 48 aircraft per month at Boeing's Seattle facility alone, with additional production lines planned for activation as military contracts expanded. Each bomber required approximately 15,000 man-H hours to complete, compared to 32,000 man-hour for a single Shinzān prototype. American workers could build 3 flying fortresses in the time Japanese craftsmen needed to complete 1 heavy bomber. Material usage comparisons were equally sobering. A B-7 consumed 5.2 tons of aluminum alloy, while the Shinzān required 8.1 tons for comparable capability. American designers had eliminated unnecessary material through systematic analysis of stress distribution, creating structures that were exactly strong enough to meet operational requirements without excess weight. That reduced performance. Japanese engineers had built structures that were stronger than necessary, assuming that excess strength was always preferable to optimized design. The maintenance philosophy differences became apparent through examining the captured bombers' logbooks, which had been recovered intact from the crash site. B-7 squadrons performed scheduled maintenance using standardized procedures that could be completed by any trained mechanic in the field. Engine changes took 6 hours using common tools, while hydraulic system repairs required only basic mechanical knowledge. Shinzān maintenance demanded specialists who understood the unique characteristics of each aircraft, making squadron-level repairs impossible under combat conditions. Most revealing was the American approach to battle damage repair. B-7 structures were designed to fail gracefully with damage, concentrated at specific points that could be patched using field expedients. Aluminum skin panels could be replaced with sections cut from other aircraft, while structural repairs used standard aluminum angle stock available from any industrial supplier. Japanese aircraft required custom parts manufactured to precise specifications, making field repairs impossible and forcing damaged aircraft out of service for extended periods. By October of 1942, Matsumura had reached a conclusion that would reshape Japan's entire approach to strategic bomber development. The B-7 was not a superior aircraft because of advanced technology or exotic materials. It was superior because American engineers had solved the correct problem. Instead of building the perfect bomber, they had built a bomber that could be manufactured, maintained, and operated by ordinary people under extraordinary circumstances. The path forward was clear but daunting. Japan needed to abandon the Shinzān program entirely and start over with American design philosophy as the foundation. But 18 months into the Pacific War, Time was running out for such fundamental changes in approach. The telegram from Imperial Navy headquarters arrived at Nakajima's Kisumi facility on September 14, 1943, bearing specifications that seemed designed more to inspire than inform. Kenichi Matsumura read the requirements twice before setting the document on his drafting table. Understanding that Admiral Yamamoto's staff had essentially ordered his team to violate the laws of physics within an 18-month deadline. Maximum speed 370 mph air, faster than any existing heavy bomber in the world. Service ceiling 33,000 ft, high enough to operate above most intercepting fighters. Range 4,600 miles with reduced bomb load sufficient to reach the American West Coast in return. Bomb capacity 8,800 lb maximum, enough to devastate industrial targets. The specifications read like a wish list written by men who had never calculated power-to-weight ratios or aluminum allocation requirements. But Matsumura had spent 18 months studying captured B-7s, and the lessons learned from American engineering philosophy had crystallized into a revolutionary insight. Japan's fundamental mistake had been copying American hardware while ignoring American methodology. The new bomber, designated G8N Renzan or Mountain Range, would abandon the DC-4E template entirely and embrace the design principles that made American aircraft successful. Working sessions that autumn stretched past midnight as Matsumura's team discarded every assumption that had guided Japanese aircraft development since the 1930s. Traditional Japanese engineering emphasized individual craftsmanship and component optimization, creating aircraft that were technological marvels, but manufacturing nightmares. American engineering emphasized systematic integration and production efficiency, creating aircraft that were good enough to build by the thousands. The G8N design that emerged from these intensive sessions looked nothing like previous Japanese bombers. Clean lines replaced complex curves. Single vertical stabilizer eliminated the twin-tail configuration that had plagued the Shinzān's directional stability. Mid-mounted wings provided structural efficiency, while improving access for maintenance crews. Every component was designed for reliability first, performance second, and manufacturing ease third, priorities that reversed traditional Japanese aircraft development philosophy. Power plant selection proved critical to the entire program's success. Instead of adapting existing engines, Matsumura convinced Navy procurement to fund development of the Nakajima NK9KL homoradial, specifically for the G8N mission. Each engine would produce 2,000 horsepower at military power settings, providing 8,000 total horsepower to lift an aircraft designed to weigh 38,360 lb. The power-to-weight ratio would finally match American standards while exceeding American performance. The Homar engines incorporated lessons learned from Wright Cyclone T-rounds, emphasizing operational reliability over peak performance. Cylinder cooling fins used simplified designs that could be mass-produced, while internal components were manufactured to tolerances that balance precision with production speed. Supercharging systems were optimized for high-altitude operation, providing full power output at altitudes where intercepting fighters would struggle to maintain formation. Airframe construction abandoned the complex forgings and custom machining that had made the Shinzān prohibitively expensive to manufacture. G8N wing spars used aluminum extrusions that could be produced on standard rolling mills with reinforcement concentrated at high stress points rather than distributed throughout the structure. Skin panels were designed for replacement using common shop tools, allowing battle damage repair under field conditions. The electrical system design reflected hard-won understanding of combat maintenance requirements. Standardized connectors and color-coded wiring eliminated guesswork during repairs, while accessible routing allowed mechanics to trace problems quickly. Power distribution used proven American-style bus systems, rather than the complex switching networks that had made Shinzān electrical repairs a specialist task requiring days of troubleshooting. Fuel system design prioritized survivability without compromising maintainability. Self-sealing tanks used rubber bladders that could be replaced by squadron-level mechanics, while fuel pumps and valves were positioned for easy access during scheduled maintenance. The system provided precise fuel management for long-range missions while eliminating the complex automation that had created multiple failure points in earlier designs. Defensive armament placement balanced firepower with structural integrity, avoiding the weight penalties that had plagued previous Japanese bombers. Gun positions used standardized mounts that could accommodate different weapon types, while ammunition feeds relied on mechanical systems that functioned reliably under violent maneuvering. The installation provided comprehensive coverage without creating drag or weight problems that would compromise flight performance. The first G8N prototype rolled out of Nakajima's final assembly hangar on August 23, 1944. Its silver aluminum skin gleaming under work lights that had burned continuously for 3 months. Matsumura personally supervised the pre-flight inspection, checking systems that represented 4 years of accumulated knowledge about what made aircraft successful under combat conditions. Test pilot Captain Tishi Shirani completed his first flight on October 23, 1944, reporting handling characteristics that exceeded all expectations. Maximum speed of 368 mph at 26,245 ft validated the design. Calculations that had predicted American-level performance from Japanese manufacturing service ceiling tests confirmed the aircraft could operate at 33,465 ft, well above the altitude band, where most intercepting fighters maintained combat effectiveness. Range testing proved equally impressive, with maximum distance of 46.39 mph demonstrated during carefully monitored fuel consumption flights. The G8N could reach targets on the American West Coast and return to bases in the Mariana Islands, finally providing Japan with the strategic bombing capability that had been promised since Pearl Harbor planning began. But even as the third prototype completed acceptance trials at Koizumi Airfield in early 1945, the strategic situation that had justified the G8N program was collapsing beyond recovery. American B-29 superfortresses were systematically destroying Japanese industrial capacity, while carrier-based aircraft ranged freely over the home islands. The aluminum needed for G8N production was being diverted to defensive fighter programs that offered more immediate protection against the bombing campaign that was reducing Japanese cities to ash and rubble. Only 4 GN prototypes would be completed before Japan's surrender ended the program permanently. The aircraft that finally solved Japan's strategic bomber problem had arrived too late to influence the war's outcome, a masterpiece of engineering rendered irrelevant by industrial arithmetic that no amount of technical brilliance could overcome. Matsumura watched the fourth prototype taxi to its parking position on August 10, 1945, knowing that American technical teams would soon arrive to examine what Japanese engineering could accomplish when freed from the constraints of copying foreign designs. The G8N represented everything Japan had learned about building aircraft the right way, but learning the right way had taken too long to matter strategically. The surrender announcement reached Nakajima's Koizumi facility at noon on August 15, 1945, transmitted through radio speakers that crackled with static as Emperor Hirohito's voice informed the Japanese people that the war had ended. Kenichi Matsumura stood in the engineering hangar beside the fourth G8N prototype, watching his team of 200 specialists absorb the reality that 4 years of intensive development had concluded with Japan's unconditional defeat. Outside the hangar, American B-29 superfortresses continued their systematic destruction of Japanese industrial capacity. Their contrails visible at altitudes the G8N could theoretically reach but would never operationally challenge. The irony was complete. Japan had finally created a strategic bomber capable of matching American performance, just as American strategic bombers finished eliminating Japan's ability to manufacture aircraft in meaningful quantities. The numbers that defined the program's ultimate failure were carved into Matsumura's memory with mathematical precision. 4 G8N prototypes completed versus 12,531 B-17 Flying Fortresses built by American factories. 4 aircraft that represented the pinnacle of Japanese engineering achievement versus an American production line that delivered more bombers in a single month than Japan had built in 4 years of concentrated effort. American technical intelligence teams arrived at Koizumi on September 3, 1945. Led by Colonel Harold Watson of the Army Air Force's Technical Intelligence Unit, Matsumura personally conducted the examination of the G8N prototypes, explaining design decisions and performance characteristics to American engineers who approached the aircraft with professional curiosity rather than triumphant satisfaction. The captured German and Japanese aircraft they were documenting represented technological achievements that had arrived too late to influence the war's outcome. Colonel Watson's assessment recorded in technical reports that would remain classified for decades acknowledged the G8N's impressive capabilities, while highlighting the industrial limitations that had doomed the program. Maximum speed of 368 mph exceeded early B-29 performance figures, while the service ceiling of 33,465 ft matched American heavy bomber standards. Range capability of 4,600 miles would have allowed strikes against the continental United States from bases in the Marshall Islands, but performance specifications told only part of the story. Watson's team calculated that manufacturing a single G required approximately 42,000 man-hours of skilled labor, compared to 18,000 man-hours for a B-29 superfortress built on Boeing's automated production lines. Japanese craftsmanship produced aircraft that were technically superior in individual components, but American mass production created aircraft that were strategically decisive through sheer numerical superiority. The material consumption analysis revealed even starker contrasts. Each G8N prototype consumed 8.7 tons of aluminum alloy, while American heavy bombers averaged 6.2 tons through systematic optimization of structural design. Japan's total aluminum production in 1944 peaked at 142,000 tons, theoretically sufficient to build 16,000 G8N bombers, if no other aircraft were manufactured simultaneously. American aluminum production in 1943 exceeded 920,000 tons, supporting simultaneous production of fighters, bombers, transport aircraft, and civilian goods without resource allocation conflicts. Matsumura found himself explaining to American interrogators the philosophical differences that had shaped Japanese aircraft development throughout the war. Traditional Japanese engineering emphasized perfection of individual components, creating aircraft that were marvel of precision manufacturing, but nightmares of production complexity. American engineering emphasized integration of adequate components into effective systems, creating aircraft that could be manufactured by workers with minimal training using standardized procedures. The engine development comparison proved particularly illuminating for American technical teams studying lessons learned from the Pacific War. NK9KL Homar radials in the G8N generated 2,000 horsepower each through supercharging systems that represented cutting-edge Japanese technology, but required complete overhauls every 120 flight hours due to metallurgical limitations and high-stress components. Wright R-3350 Cyclones in the B-29 produced 2,200 horsepower while operating for 400 hours between major maintenance through systematic reliability engineering that prioritized operational availability over peak performance. Manufacturing philosophy differences extended to every aspect of aircraft production. G8N wing spars were machined from solid aluminum billets using precision tooling that required hours of setup time for each. Component B-29 wing spars were assembled from aluminum extrusions and sheet metal, stampings that could be mass-produced using automated machinery, operated by semi-skilled workers. Japanese methods produced structurally superior components, but American methods produced adequate components in quantities that overwhelmed any performance advantages. The maintenance requirements analysis revealed operational realities that had been invisible during peacetime development. G8N systems required specialized tools and trained mechanics for routine maintenance, making squadron-level repairs impossible under combat conditions. B-29 systems were designed for maintenance by mechanics with basic training, using common tools available at any forward airfield. A damaged superfortress could be returned to combat readiness in hours, while a damaged G8N would require weeks of specialized repair work at major maintenance facilities. By October of 1945, American technical teams had completed their documentation of Japanese aircraft development programs and reached conclusions that would influence post-war military procurement for decades. Technical excellence without industrial capacity was strategically meaningless. The most sophisticated aircraft in the world could not compensate for fundamental limitations in manufacturing capability and resource allocation. Matsumura's final interview with Colonel Watson took place beside the fourth G8N prototype on November 8, 1945, as American transport crews prepared to ship the aircraft to Wright Field for detailed analysis. The conversation focused not on technical specifications but on the systemic factors that had determined the war's outcome, despite Japanese achievements in individual aircraft performance. The devastating arithmetic of industrial warfare had rendered engineering excellence irrelevant. More B-7 flying fortresses had been shot down over Germany. 4,750 aircraft than Japan had built of all heavy bomber types combined throughout the entire war. American factories replaced combat losses faster than Japanese factories could produce new aircraft, creating a mathematical impossibility that no amount of technical sophistication could overcome. Watson's final assessment recorded unclassified reports that would shape American understanding of industrial warfare for the Cold War era, emphasized lessons that extended far beyond aircraft development. Victory belonged not to nations that built the best weapons, but to nations that built adequate weapons in overwhelming quantities. The G8N Renzan represented everything that Japanese engineering could accomplish when freed from resource constraints. But resource constraints were the fundamental reality of modern warfare. Matsumura watched the fourth prototype disappear into the cargo hold of an American transport aircraft. Understanding that his team's greatest achievement would serve as a museum exhibit rather than an operational weapon. 4 years of intensive development had produced an aircraft that could have changed the war's trajectory, if manufactured in quantities Japan was never capable of achieving. The lesson learned too late was simple: